and I recorded 7th period, and I'm going to put it up on the Weber State thing because I will not be here after school today, and I will not be here Friday. But I will be here Monday morning. So that'll give you another review that you can look at. If you need extra help, you can come Monday before school, and you guys are lucky because you can come during tutorial too. So if you need extra help. We're going to go through everything on the list today and hopefully make it so it's very easy for you to study for the test and know what you need to do. All right. So first up, I want to take any questions that you guys came up with, and then I'll go through the list. So, yes. Yes, they're right next to the Gen Chem crate. Any questions that you came up with that you just were struggling how to do?
I'm not struggling how to do, but have you seen the test yet?
Yes, that's why I made this salmon colored piece of paper.
So this is all stuff we'll need to know?
Yes.
Okay. That's what I was
Okay, there are 3x5 cards above the computer. You're welcome to grab one of those.
Can we do that in pencil, or does it have to be black pen?
That can be whatever, but you have to be it has to be handwritten, and you can only use one side. Okay? All right, so let's just go ahead and start with the salmon colored piece of paper. First of all, it's a 30 question multiple choice test. And you'll notice there's only 18 things on this list, so there's going to be some that have multiple questions on. All right, so the first thing is when you're looking at the periodic table, here's hydrogen. Okay, we've got this little block thing going on here, and this coming up here, and this down here. How do you decide where the metals, nonmetals, and metalloids are? The line like what? Okay, boron. Okay, we call it the staircase. So it just goes like this, coming down like this. And this one down here is unanoctium, which is octium, it's ogdicin now. Okay, OG. But we're going to do these. Let's see, silicon, arsenic, tellurium, and astatine. And then you have two others that support it underneath, okay, which are germanium and antimony. SB, sorry. So you can't really see those, but those are your metalloids. This Og is not one. There's 7 of them. 7 of the metalloids. You'll want to make sure that you know them. So you're going to make sure that you know these 7. And the easiest way to do that, like he said, was just basically draw a line between boron and unanoctium. I'm having a hard time. It used to be unanoctium. Okay? And all of those will count on that staircase. It's just a staircase down except for ogdicin. And then underneath the second and the third one, you have a support system, so germanium and antimony. So just remember that those are your metalloids. What is special about metalloids? I cannot spell today. I am so sorry. So they have properties of both metals and non-metal, right? But there's something really special about them. Does anybody know? They are what we call semiconductors. Okay, that's why we have computers, right? If we didn't have semiconductors, we couldn't have computers. All right, what is on the left of... Good. So from here, including all of this, these are all considered metals.
I remember, because metal starts with M, and mostly metals. So, most of the periodic table.
Right, most of the periodic table is metal. So basically, all of this, nice and pretty blue, is metals. Okay, what's the other side? Oh, well, let's go through properties first. Hydrogen is considered both. Hydrogen is sort of its own thing. So she won't ask you about hydrogen because it can act like a metal in lithium's column, but it can also act like a non-metal in fluorine's column. So it sort of floats above. Okay, so let's do some properties of metals. Tell me some things about metals.
They're a good conductor.
Okay, they are good conductors of both heat and electricity. Okay, what else? They're solid except for one, which is what? Mercury, also known as quicksilver, is a liquid. Okay? What else about them? They're shiny. Okay? They have luster. That means they're shiny. They reflect things. What else? They're ductile. Does anybody know what that means? You can pull things into wires. So if it's ductile, you can pull it into a wire. Malleable. Anybody know what malleable means? Okay, I can hammer it. I can make it so it will go into whatever shape. So these are all properties of metals. You need to know the properties of metals and metalloids. We also need to know the properties of these guys over here, which are what? Good. Nonmetals. So what are some properties of nonmetals? We actually have gases, liquids, and solids in nonmetals. Okay, what else? Okay, they are, you can say they're sort of crumbly most of the time. That is crumbly? I don't know how to spell it. Okay, but you got to be careful because carbon also makes diamonds and graphite and stuff like that, so you got to be careful when you say crumbly. There are exceptions to the rule. Okay, so they're often powdery. They shatter. So when you try and pound them into a shape, they'll just shatter. These are insulators. So they don't conduct electricity or heat, they actually stop it. Okay, can you think of anything else? Okay, let's go on to the next one. Be able to know how to read and interpret nuclear and hyphen notation and determine the number of protons, electrons, neutrons, atomic number, and mass number. This is where most of the classes have been struggling today, so we'll spend a little time on this today. When you look at a nuclear symbol, say that I wanted FM and I did 101 and it had a +3 charge. If I were to ask you, okay, first of all, what's the mass number? What would the mass number be? 101. And I probably did that wrong because let's do 201 for that. So let's do 201 because I was thinking the atomic number. Atomic number is what? This one's easy because it's like the station. FM, your grandparents' station. FM 100. Okay, so FM 100. Here then we go from protons, electrons, and neutrons. So protons, how many protons do I have? I have 100 because that's equal to the atomic number. What is the number of electrons here? How'd you get that? So, okay, good. In other words, I've got 3 more protons than I do electrons, right? Because remember, protons are positive, electrons are negative. So if I have a positive charge, I have more protons than electrons. If I have a negative charge, I have more electrons than protons. So because I have a +3, I have 3 less electrons, so 97. How do I get the neutrons? It would be 101. You would take 201 minus 100, and it gives you 101. So you take these two subtracted to give you neutrons. Okay? All right, now I've done one. I'm going to have you do 2 others. One's going to be in this form, which is called nuclear isotopic symbol, and the other one's going to be in hyphen form. The hyphen form usually does not have a charge. So what does that tell you? If it doesn't have a charge. The electrons and protons are the same. Okay, so here we go. We're going to use samarium, and we're going to use 171, and we're going to call it plus 2, and then we're going to use arsenic, and we're going to call it 76. Okay, I want you to find all these things. I'm just going to make a table. Be easier. Okay, take a second. I'm going to be asking you, I'm going to be pulling your names, making you answer me. So everybody do it. If you don't know how to do this, ask a neighbor, because you might have to answer it. SM is in the F.
Oh, yeah, it's right here.
Okay, we ready? They had a chance? Okay, Kyle, what is the mass of samarium? Mass number? 171. Okay. Is Alex here? Okay, Jesus. Give me the atomic number. 62, good. All right, Jaron, give me the number of protons. 62, good. All right, Caleb, give me the number of electrons. And Ashley, give me the number of neutrons. 109. Okay, if you got all these the same as here, thumbs up. If you didn't, thumbs down. Okay, let's see what we can do with the next one then. All right, going down on this one, arsenic. Kaylee, what did you get for the mass number? 76, thank you. And Aspen, 33 for the atomic number. Okay, and Tyson, 33, good, for the number of protons. And Cambry, number of electrons. Okay, can somebody help Camry? Yes? 33. There's no charge on this one, so they're all going to be the same here. Good. All right, Emma, what do we get for neutrons? 43. Okay, thumbs up if I got all those. Thumbs down if I didn't get all of them. Okay, let's do a couple more because I want to make sure that you understand. I'm going to do a negative one so you can get that one done too. And then I'll give you a few seconds to do it. So here we go. Nope, never change your protons. Always change your electrons. Let's do. Okay, take a minute and get those done because I'm going to be asking you. Make sure you check with your neighbor. Mm-hmm. Okay, ready? Okay. All right, let's see. Richard, what's the mass number for aluminum? 27. Emma, what's the atomic number for aluminum? Good. Luke, what is the protons? Is Luke here? Yeah, okay.
I did the wrong one, sorry.
Uh-oh. Can you do do it real fast? 13, good. Okay. And Brian, electrons. 14. Do we agree with that? 10. Okay. Since you have 3 more protons than electrons, because you have a positive 3 charge, you got to subtract it. See that? Okay. Neutrons. Let's do Ben.
I forgot, I didn't realize we have 3, so it's 14.
It is 14. Okay, thumbs up, I got these all right. Thumbs down, I didn't. It's okay. All right, so let's go to the next one. Kyle, mass number. Okay, Alex is not here. Jesus, atomic number. 27? Okay, Jaron. Good. I'm just going down the road here. Caleb, electrons. And Ashley, neutrons. You always get the hard one, sorry. Okay, everybody agree with that? All right. So you need to be able to do it whether it's positive or negative. Oh, we forgot to do arsenic. Let's keep going. Kaylee, let's do mass number for arsenic. 79. Aspen, atomic number. 33. Tyson, protons. 33. Cambry, electrons. Not quite. Somebody help her out? Electrons. 36. Okay, what you want to do is we've had a couple problems here. So if you have a negative number, you have to add it to the number of protons because you have to have more electrons. You can't change the protons. If you have a positive number, you've got to take it away from the protons because you have more protons than electrons. So this would be 36. Okay? Okay, see how that works? It's sort of backwards. Yeah, it's backwards. Okay, and then Emma, tell me how many neutrons. 46. Everybody okay with that? Okay, got it right? Didn't get it? Okay, so we do have some issues a little bit. Watch the numbers again. If it's a negative, that means I have more electrons. If it's a positive, that means I have more protons. Protons you cannot change. The only thing you can change is electrons, right? To get charges. Okay, going forward. Get back to my paper here. Do you feel comfortable with the nuclear symbol? Okay, in the nuclear symbol, we have this number, and then we have an A and a Z. She will refer to them as A and Z. You need to be able to know what they are. A is the A is the mass number. Z is the atomic mass, or atomic number. Sorry. A is the mass, Z is the atomic number. So when she's talking in a sentence and she says something, you need to know what they are. So mass number is the number of protons plus the number of neutrons. It's a plus. Atomic number is equal to the number of protons. Okay? And then right here, if there's a charge, that will tell you how many the number of electrons are. So if there's no charge, protons and electrons are the same. But if there's a charge, then you have a difference in the number of electrons than there is protons. Okay, less electrons means you're going to have a positive charge. More electrons means you're going to have a negative charge. Everybody okay with that? Okay, now, we need to know what an isotope is. So what is the definition of an isotope? Somebody help me. Isotope. Okay, multiple masses is the same thing, so give me a little bit better definition. Somebody.
It's a version of the atom that has the same number of protons but different mass.
Okay, so same number of protons, I'll take that. Same number of protons, but different number of what? Neutrons, leading to different mass numbers. Right? Okay, so you got to understand that the protons, they are the identity. They tell me what element I have. I cannot change that without changing the element. Okay? So if I change the protons, I change the element. But if I change the neutrons, I just change the isotope. If I change the electrons, I change the ion. So it becomes a different ion. Okay? All right. The next part is being able to do what we did in our lab. What was that lab about that we did? Mass spectrometry, yes. So what was mass spectrometry? Yes?
Wasn't it like when you had the different like isotope stuff and you're trying to find out the average?
We did. We looked at the different isotopes. So we did it with colored cereal. We made a graph that maybe looked like something like this. I don't know, right? And what we did in the first one, in the pre-lab, is we measured these heights of these peaks, and we added up all the peak heights together, right? And then we took each individual peak and divided by the total, and we were able to get what we call a fraction abundance, right? She might give you a fraction abundance, but she also might give you a percent. The only difference between fraction abundance and a percent is what? Percent I've times by 100. Fraction abundance is under 1. Right? So we add up to equal 1 or 1 whole for fraction abundance. For percent, we add up to equal 100%. So all we've done is times it by 100. Okay, so she will have word problems. Okay, she's not going to be nice like I'm going to be here in just a minute and give you, here's the isotope, here's the percent, here's the isotope, here's the percent. But she'll have it in word problems. So she'll come along and say, this element X, that's 79 here, is about 80.36%, and its mass is 78.974. And then she'll have a comma. And then she'll give you another one. I'm not going to write the whole words out, but that's what she's doing, okay? So she says this isotope, this one, has a percent of 19.4, make sure I'm getting this to 100%, and its actual mass is 70.764, I don't know, whatever. Okay, she could give you a whole bunch in a row, but she's separated by commas. The key here is to take and write it down on your scratch paper. Make sure you took what was before the comma as one thing. Does that make sense? Don't get it mixed up. Because that's where a lot of kids go whacked a little bit on their problems, is they'll miss the comma. So make sure you're watching the comma. How do I do this? All you're going to do is times these two together, add it to these two times together, get an answer. Go ahead and do that. Let's see. If you haven't got a calculator, I got some on top of the computer. You can grab mine and use it for a minute. So once we get an answer here, you're actually going to take that answer and divide it by 100 to get it out of percent to get your final answer. Here's a key. The answer should be between these two numbers. If it is not, or between the numbers that you've got listed. If it's not, I did something wrong, redo it. The other key is looking at which one is the most abundant. This one has 80%. So it should be closer to the 79 than it is to the 71. Otherwise, I've inputted it wrong. So there's two checks that you can do on problems like this. Okay, what did we get? Somebody got it done? 77.36. Is it what we said? Is it between those two numbers? Yes. Is it closer to the 79? Yes. So I know that I've got it right. So then I can go and look for her answers, what she's got, and find it. Does that make sense? Okay, now, there might be problems where it goes like this. Here's this isotope X, and it is 20.36%. And you have another isotope, 61. And that's all she gives you. And you're supposed to find the average AMU. How do you go about doing it? You assume the other one's what? The rest of the percent to get 100. So I take 100 minus that, and that would give me this percent, right? So I should end up with 79.64% for this, right? But they didn't give me the mass. What do I do now? This is your mass. That's what you're going to use. Okay, so you're going to take 56 times 20. You're going to add to it 61 times 79. When you get that answer, you're going to take that answer and divide it by 100 again to get it out of percent. And we should end up between these two numbers. What one should it be closer to? Should be closer to the 61. So let's do it. Let's see what we did. Do you get it? So 56 times 20.36 plus 61 times 79.64. Get an answer divided by 100. What do we get? $59.98, which is almost 60, which is really close to that, right? So we're good. Awesome. Okay, so we should be able to find that real fast. Any problems with that? You want to do another one, or are you okay? Thumbs up, I'm okay. Thumbs down, I want to do another. It's okay, you don't have to look around to others. I got some sideways. Let's do one more. Okay, so here we have, I'm going to call T. We have a 33, a T30, and a T28. We're going to do 3 this time. This T30 has 15.56%, and it's actually 32.978. This T30 here has 39.45%, and it's really 29.123. And now I got to use a calculator because I went numbers I don't know. The rest is going to be the other one. And this is going to be 27.9297. There we go. I just made it up. So to get the other one, all we have to do then is take 100 and minus, oh, this one's pretty. 100 minus the 15.56 minus the 39.45. I got 44. 44.99 left over. Okay, do it one more time. I got it right here in front of me, but yeah, it should be 44.99% for this. Yeah. Okay, so now all you have to do is take these three times them by each other, add them to each other, get an answer. Once you've got your answer, divide it by 100. Okay, before we plug it in, though, this is what I want you to do when you do it on your test. Before you plug it in, what number should it be between? 33 and 28. Which one should it be closer to? Should be closer to the 28. Okay, go ahead and do it. Let's see what our answer ends up being. Okay, who's brave? Who's got it done? Okay, what is it? 2908.
Yeah.
Is that what everybody else got? 29.1? 19? Okay, so that was close, but I think we got two that did this. So this would be the grams. And it is close. It's between these two, which are the high percentages, which is good. Okay, can you see how this is working? Okay, now she's also going to look at you and say, okay, or give you a question that says, all right, the relative average AMU for a compound is, say, 28.0276. The isotopes are X 24, X 26, X 28, and X 30, and X 32. Which is the most abundant isotope? 28. So all you've got to do is look at the number that they gave you and which one's closest to it. Okay? Don't make it harder than it is. Okay? She'll put a lot of different words in there. I bare boned it. Okay? It means I didn't put all the little fluff in there. I bare boned it. But she's basically going to give you an average AMU, and she's going to give you a whole bunch of isotopes, and they're not going to be close together because you can't look at it just like what you did here. But she's going to ask which one's the most abundant. Just look for the one that's closest to it in mass. You don't know that. You've got, yeah, it could have done that. Well, it wouldn't be 30 and 32. It would have to been 26 and 30. Yeah, it could have been. But she said, what would, I think, you know, she basically asked, what do you think would be the most average? Or what do you think would be the most abundant by the mass? And it's pretty obvious. For instance, like if you take lithium, and you knew there was a lithium-6 and a lithium-7, which one would be most abundant? 7, because the mass on lithium is 6.94, so it's closer to 7 than it is to 6. Okay, look at nitrogen. If you don't know there's a nitrogen 14 and a nitrogen 15, which one is it closer to? Nitrogen 14, right? If you look at silver, and you know there's a silver 107 and 108, which one's it close to? Okay, so that's what you need to be able to do, okay? All right, so let's go down to the next one. Where am I? Must have been an isotope. Oh, you have 11 elements that have Latin or German names. So their symbol is not the same as their name. What are they? Yes? Gold. So gold is AU. What else? Iron. Fe. Silver. Ag. Antimony. Antimony. Sb. Tungsten. W, lead, Pb, potassium. Whoops, I did the M and the U together. K, mercury. Have I got them all yet? 10, no. That's an SN, by the way, if you can't read it. Okay, these right here are the most common for kids to screw up on. They say potassium's P. It's not P. That's phosphorus. They say sodium is S. No, that's sulfur. So that's the most common mistaked ones. Even on when I'm reading the AP tests, those are the biggest mistakes, and that costs them their grade on the AP tests. So, yeah, so she is really particular about these, so make sure you know them or put them on your card. All right, next thing, be able to write the element symbol correctly for any given atom. So if she's asking you for, if she's asking you, I'm just going to go like this, for an element that has protons of 15 and neutrons of 16, and electrons of 14. And I don't even know if that's a real element, but we'll pretend. Okay, you need to be able to write the symbol. So how do I write the nuclear symbol for this?
You find whatever 13 is phosphorus.
Okay, so I'm looking at 15 for the atomic number, so that's phosphorus. Okay, and I'm going to be off on the charge, but that's okay.
And then, with the charge, it's going to be +1.
Okay, so it's going to be a +1 because I have one more proton, then I have electrons. What else do I need to write for the nuclear symbol?
Mass number is going to be.
Okay, my mass number is taking these two and adding them together. So that's going to be 31, and it goes here.
Your atomic number is going to be.
My atomic number comes from the number of protons, and that's 15. It goes here. Okay, I'm going to give you another one that you're going to write now. Okay, am I okay to go forward? Okay, so here's yours to try. So, protons. Okay, I'm going to be asking you for different parts of it. Give you another minute here. See if you can do it. Remember, you've got to tell me what element it is, too. Okay, you've got to use the element symbol.
So how come on that periodic table 113 is the unusual number, but on this one 113 is no?
Because from when we did this to when we did that, it actually has a name now.
Oh, so they found another.
No, they've actually been able to redo it, yes.
Oh, so they found a use for it. So with
Not
that-
use, they've been able to reproduce it.
Yeah, when that one was put up, they only had it once, right?
Right. Okay, Brian, tell me what symbols we're using. TM, capital T, lowercase m. Make sure the second letter is always lowercase. Okay, Richard, tell me the mass number and where it goes. Top left, 170. Okay, Luke, tell me the charge. +3, where does it go? Top right. Okay, and Kaylee, tell me the atomic number and where it goes. 69, good. Okay, did anybody have problems? Let's do this. Thumbs up, I understood how to do this. I did it right. Thumbs down, I didn't. Thumbs sideways, I missed one or two things. Okay, you really need to be able to do this. So hopefully you're getting this, understanding how to do it. All right, let's move on to the next one because time is not our friend today. Okay, we are now on to understand and read a chemical compound. So if I have a compound, say that I put up CH4. Tell me what that means. 1 carbon, 4 hydrogen atoms, right? Atoms. Total atoms is 5. If I put up a compound C6H12O6, that is sugar. Okay? 24 atoms in total, and if I said how many atoms of oxygen? 6. Okay, what if I put up this compound right here? That's hydrogen peroxide. Okay, yeah, don't drink that. You die. Good for infections. Swirl it as long as it's bound 1%. If you go up to 30, then you'll rip off all things anyway. What happens if I say this? That's a total of 6 atoms, right? How many magnesiums? How many sulfurs? How many oxygens? Good. So you need to be able to write it. So if I told you out loud that I have 3 hydrogens, 1 phosphorus, and 4 oxygens, how would I write that? H, P1, phosphorus 1. So I put a 1? Okay. And then oxygen 4. O4. Okay. So you need to be able to read something and be able to put it into chemical form. Okay? All right, next one. We're going down to understand read. Now we're going down to know the family groups on the periodic table and be able to know the elements. This was our lab last time. So we have this, we have, whoops, I don't want to put that there. We have this, we have, I exaggerated the P, sorry. Gets really exaggerated. Okay, so we worked with flame test with this first column, which is called the alkali metals. And these alkali metals are very reactive. We did several flame tests as we came down. We did lithium and it was red. We did sodium, it was yellow. We did potassium, it was light purple. We did rubidium, it was bright red. This is a very reactive family, especially with water. As I go down the table, it gets even more reactive. So lithium, if I put lithium in water, it will sort of sit there and bubble. If I put sodium in water, it starts fuzzing around a lot, and I sometimes will get a yellow flame. If I put potassium in water, it starts bouncing around, and I get bright purple flame, and all of a sudden it'll explode. If I put rubidium in water, I got an explosion right away. If I got cesium in water, I could put it in a bathtub and destroy the bathtub with just a part of a gram.
What about francium?
Francium doesn't hang around long enough for me to get it in there.
What does that mean?
Its half-life, or its amount of life that it's alive, is like 0.0001 of a second. So it's not alive long enough to do anything with water.
So how do you
Okay?
get cesium?
So lots of money. Yeah.
What if you have a lot of money? How do you get it?
You have to go through the channels to get there because it's not one that you can get
This
over the counter.
get it from-
You have to have a university get it to be used for testing and da-da-da-da.
Oh, so we can have it.
Oh, no. I wouldn't want to be responsible for that one. Okay, so the next column over is alkaline earth metals. And this family is more calm. It will react with water, but it's more calm about it. It does it over time. It's sort of just bubbles, and it actually will form bases when it's formed with. So all of these will form bases when they mix with water. But they're more calm. We also did test them in the lab. Magnesium, you should have seen a more of white flame. Calcium, you should have seen a yellow flame. Strontium, a red flame, and barium, a green flame. So hopefully you saw that in lab. So you need to be able to describe where these families are on the periodic table and sort of see them in your mind's eye and what's going on with them. Okay, the next family that she talks about in the chapter is the transition metals. And that's this big thing here. And these guys are like the, friends to all. They'll just hang around with anybody. The intertransition are down here in the F. And these intertransition are, for the most part, rare. They used to call them rare earths because they're hard to come by. They're hard to separate. A lot of them, they didn't know they were two of them because they were so close in properties, they thought it was the same element. Then we tested a few from oxygen. We did oxygen, nitrogen, and then we did fluorine's column. We didn't do fluorine, but we did chlorine, we did bromine, we did iodine. And this column right here is known as the halogens. The halogens are very reactive. They like to make compounds. You cannot find them on the earth free. They like to make compounds, yes.
They react the most with the alkaline metals.
Yes, they're very reactive with the alkali metals. When those two get together, alkali likes to give away one, halogens like to take one.
So what
Okay.
happens if you had a halogen and alkaline?
It's an explosion. There's actually a YouTube video where they put sodium and chlorine gas together, or sodium metal and chlorine gas, and it explodes and you get salt, and he salts his popcorn and then eats it.
It seems like a dangerous way to make
Yeah, I think so too.
You should try it.
I don't think so. No, I can't get that. Okay, here you got the noble gases. These ones and the halogens we tested in the cathode ray tubes in lab, and you were able to see the colors. The noble gases were the ones that were the brightest. The neon, the krypton, the argon, xenon. These were the ones that were the really bright colors. The chlorine, bromine, iodine, they were a little bit dimmer. Okay, so when I think of noble gases, I'm the king, you know, and they want to let everybody know they're shiny. They don't like to react. They often are called the inert gases because for a long time they thought they didn't react, but we can force them to react now. Okay, we did look at nitrogen. We looked at oxygen. Oxygen was the dimmest, if you remember. It was the really, really dim one. And we looked at some compounds. There's one other one that we need to worry about. Carbon is what it goes into in your chapter. Carbon is very special. That's halfway through the periodic table as far as the valence electrons. So it's a 4. It can gain 4, it can lose 4. And because of that, it has some interesting properties. It can go together to make a diamond, which is very, very hard. Or it can make graphite, which is layers that slide on each other. Or it can make coal, which is sort of mix of both. Or it can make carbon dioxide, where it has 2 bonds on one side and 2 bonds on the other side. It is very versatile. Okay? It can make what's called a buckyball. So if you take a soccer ball and at every corner on the soccer ball put a carbon atom, that would represent what a buckyball is in a carbon atom. And they're using buckyballs and nanotubes where they take and slice that buckyball apart and make it elongated like a pill shape, where they put chemicals inside, and then on the outside they attach a chemical that will attach somewhere in your body, so they can take and give you a pill, and it goes directly to wherever it is needed in the body, attaches, breaks that pill open or buckyball open, and the medicine is delivered right where it's needed. So they're working a lot on that. Excuse me. So carbon, you need to know, is a unique family. It can go with either or. It's sort of like the mediator of the periodic table, because it goes with both the metals and the nonmetals. It can work with both of them. Okay, so next on the thing here. If I'm skipping any, please let me know, because I am all over the place and I'm trying not to be. So, lung properties, including that they contain same number of valence electrons. Okay, so valence electrons. Valence electrons are just the S and the P. 1, 2, 3, 4, 5, 6, 7, 8. We ignore the D and the F when we're talking about valence electrons. It's just the S and the P. Just the S and the P. Okay? In the DRF, it still has 2 valence electrons, because we just worry about what's on that row to get to that element in the S and the P. Okay? There are some exceptions to the rules, but you are not held responsible right now for that. The ones that are almost full will still run from the S, or the ones that are almost half full will still run from the S. So then it makes it 1 valence electron. But we're not going to worry about it. Okay. Understand how valence electrons affect reactivity of an element. So all elements want to be a noble gas, right? If I'm going to be a noble gas, I got to have 8 in my outer shell. Halogens are 1 away from getting 8 in their outer shell. So they're very, very aggressive about getting that one. Excuse me, I'm going to get a drink of water. It's tickling my throat. Pardon me. Okay, they're very, very aggressive about getting that one to become a noble gas. The other one that's really aggressive is column number 1, because if they lose one, they become like the noble gas below them. So if I lose one and I'm potassium, I become like the noble gas argon.
And they want to do that?
Yeah, I want to be a noble gas at all costs. If I have to give something up to be a noble gas, I will do it. If I have to gain something, I'm going to rip it off. So the most aggressive on the periodic table are 1 and 7 as far as valence electrons go. Those are the most reactive. Then it goes 2 and 6, and 3 and 5, and the last one is 4. It's still reactive, just not very reactive. Think of it this way. If I am a parent and I have one kid, and I want to go out on a vacation with my husband for a little bit and leave the kid home, finding a babysitter for one kid, pretty easy. Most people will take one kid for a while. 2 kids, a little bit harder. 3 kids, are you kidding me? You got to take it to 3 different families because they don't want that extra burden. 4 kids, haha, good luck, right? So it's a little bit harder. I have 4 kids, yes.
So did you have to split your kids for daycare or babysitting?
No, I stayed home until they were in school. So I taught before they came, and then once they came, I stayed home. They were sickly. We were down at primaries a lot. So, okay, so most reactive, 1 and 7. What about 8?
He's chilling.
He is not reactive at all. He is the least reactive on the chart because I'm already there. I'm the king. Nobody's better than me, right? So they're the nobles. All right, going down. Next one. Know the maximum number of electrons in each shell. So here's the nucleus of the atom. Here's the nucleus. 1 level out. How many electrons? 2. Next level out. How many electrons? 8. How many out next level? 18. Next level. Whoa, hello. Didn't want to go there. 32. Okay, what if I don't remember this? You can easily find it from the periodic table. Okay, here it goes. First level. 1, 2. Right? Second level. 1, 2, 3, 4, 5, 6, 7, 8. Right? Because there's 6 across the P. Third level. 1, 2, 3, 4, 5, 6, 7, 8. But then the first level of the D is also a 3. So I had another 10.
So that's how many electrons are on the shell?
Yep. So we always have 2 over here. There's always 6 here. There's 10 across here. And there's 14 here, right? When we get to the next level here, for 4, we've got 2, 10, 6, and we bring in the first of the F. That's how we get 32. Does it make sense? She probably won't ask you past that, but she might.
Is the next one, right?
Theoretically, something. 60-something. 64, I think it is, yeah. Some weird number. Okay, know the difference between columns and rows. So columns are families or groups. Rows, what are rows? So rows are periods, but they're also, there's the shells. Shell out from the nucleus. So if I'm on row 1, I'm 1 level out from the nucleus. Shell 1, shell 2, shell 3, on down. Okay. Be able to identify an element by its orbital notation, electron configuration, or noble gas notation. So I'm going to give you 3 different elements. 1 by orbital, 1 by electron configuration, and 1 by noble gas configuration. I want you to figure out who it is because I'm going to call you random. So here we go. Yeah, you can work together. But you might want to try and do it on your own first. Don't say it out loud. Let everybody have a chance. Yes. Yes. Okay, let's see. Who's the lucky winner? Mm-hmm. It will be up on the thing too, so. Okay, Brian, can you tell us what the first one is? Iron. Everybody that agrees with iron, thumbs up. How did you tell it was iron?
I didn't count, I just did it 3p on 6.
This is where you want to look. If you know where the 3D is, you just go to the 3D. How many is in the 3D? 2, 3, 4, 5, 6, right? Counting across 6 on the 3D. 1, 2, 3, 4, 5, 6. You get to iron. Okay? I don't have to do all the rest of it. I just have to look at the end when I'm identifying. If I have to do the orbital notation, then I'm going to have to do that. Okay, let's see. Ashley, what is the second one's? dy. Dysprosium. If you agree, thumbs up. Okay, again, look at the very last thing, 4F10, and 4F is the top of the F. There's 14 across, so I can count 10 this way, or I can take away 4. 1, 2, 3, 4, and it should be this one, right? Because this would be 11, 12, 13, 14. So it's dysprosium. Okay, Jaron, what is the last one? You don't know. Okay, let's see if I can get you somebody to help. You can help? Okay, Caleb? Thallium? TL, sorry. I did thorium. Okay, thallium. So again, I look, here's the key right there. Right here, the last one, 6P1. So I go down 6 rows. 6 rows is this one, and I'm 1 into the P. Okay? Let's try and do some orbital. Did we do orbital notation in that yet? I can't remember.
Not in this, but we...
In this review?
Yeah, not in this.
Okay, let's do it in the review because I can see some of you are still a little bit lost on that. So say that I was given phosphorus and I needed to do its orbital notation. I always have to start at the top with hydrogen. So as I'm looking at my periodic table here, okay, lovely periodic table. Here's hydrogen, here's helium, here's down here. These should have been numbered. Okay, when I get here, it changes numbers by 1 to go into the D. So 3, 4, 5, and 6. F is 4 and 5. When I come back over here, it goes back up. 2, 3, 4, 5, 6, 7. Okay, so I'm always starting with my hydrogen right here. This is the first row, and it's the S block, right? So I go hydrogen in, helium in. So now I've done that and that. I'm trying to get down to phosphorus, which is down on the 3rd row, about right there. So I've got to come back over here to the 2nd row, and I'm going to go through these right here. To do that, I am going to say it's the 2nd row. I'm still in an S. I'm going to go up and down. That's lithium and beryllium. Then I'm going to come over here, and I'm going to go through the 2p. So over here, there are 3 orbits in the 2p. 1, 2, 3, 4, 5, 6 across the 2p. Everybody following me so far? I'm not got to phosphorus yet, so now I'm going to have to come back and go to the 3rd row. On the 3rd row, I hit the S. The S has 1 orbit. I go up 1 and down 1 into the S. That takes care of sodium and magnesium. I'm still not to my phosphorus. So then I come over here to the 3p, 1, 2, 3 orbits in the 3p, and I count over to phosphorus. It's 1, 2, 3 to get into phosphorus. So I go 1, 2, 3, 1 in each room before you pair it up. Okay, and I'm done. Do you all understand how to do that? Is there anyone that doesn't understand? You can hold it in front if you need to, if you're embarrassed. Okay, to do the electron configuration, you just shortcut it. So say I wanted to do the electron configuration for selenium. I would go 1s2, going through the first row, 2s2, going through the second row s, then I hit the second row p, I go through all 6 of them, I'm still not to selenium. Go to the third row, I hit the s, I go through both of those 2 and I haven't hit selenium. Then I hit the third row to the p, and I have not hit selenium, I don't think. Yes, I have. No, haven't yet. It's in the fourth row. 6. Then I go to the fourth row, hit the S. I'm just following the numbers on the periodic table. And I go through those 2, still haven't hit it. Now I'm right here, and I hit the 3D. The 3D, I go all the way through, and there's 10 across there. Then I hit the 4P, and I'm how many into the 4P to get selenium? 4. So I just put a 4 there. Done. Now, what if I had to do metronymium? Bottom row in the D. Okay, it's 109. I don't want to do 109 arrows. I don't want to do that because it's really long, the electron configuration, so I want to do the noble gas configuration. So when I do the noble gas configuration, I think, oh, Price is right. Which noble gas is closest to, without going over, metronymium? And I say, oh, it's like radon, right? And I just start there. Go to the 7s, there's 2. Go down to the 5F, and I go all the way through that bottom row, 102, to nobelium. So there's 14. Then I go back up to the 6D. How many into the 6D am I? Count again. 7. Now, I can't leave it that way because the noble gas configuration says I have to do it by shell out. So I have to look at these numbers and put them in order of shell out. So, radon, then 5F14, then 6D7, then 7S2. The reason I do that is because that puts my outermost electrons at the very end, and those are the ones that are going to react with other chemicals. So they're on the very end, so I know where they're at. Okay. It says know where the S, P, D, and F are, and I've been using them. So this is the S. I always do my S in yellow, but you can do it in whatever color. S. Then we've got the P, and I always do my P in pink. That's that last 6. So if you haven't already figured that out, that's the P. And then we've got the D in the center. You can do whatever color. You should have colored these with your, if you watch the videos. And then we've got the F down here. What things do we need to know about each of these groups? How many orbits does the S have? 1. How many orbits does the P have? 3. How many orbits does D have? 5. How many orbits does the F have? 7. And if you want to find out how many electrons they have, times that number by 2, right? Because every orbit can only hold how many electrons? 2. Be careful, because if she says on a question, how many orbits or how many electrons does a 3D orbit hold? If she says orbit, it's always 2. If she says a 3D sublevel, then you would say how many? 10. If she asks how many orbits are in a 3D sublevel, then you would say 5. Okay, so be careful how she's saying it. Okay, be careful how it's worded. Make sure you understand what's going on. Okay, so the shape of the S. What shape is the S? It's a sphere. Okay, what shape is the P? Like a dumbbell or infinity. It's like 2 balloons hooked together. Okay, because it's the outside skin of the balloons. What about the D? I did it green on purpose. It's like a clover leaf. That helps me remember. and there's 4 of them that are like that, and there's one that's got sort of like a donut around the center. And then the F is got 6, I can't ever do 6 balloons hooked together. So it's really squishy, and it just moves on different orbit, on different things. Okay, so that takes us through where the S, P, D, and F block are. Next, get a clean sheet here. We're looking at the periodic table again. Gee, I wonder, this whole thing is about the periodic table, huh? Okay, when we look at trends on the periodic table, we always want to go from francium to helium. Okay? There always is a trend here diagonal between francium and helium. If I look at francium, this is the largest atomic radius. The way I remember it is francium is fat. Francium is fat, so it's going to be the largest. Okay? So that means helium is the smallest, right? Atomic radius. Wait a minute, what about hydrogen? What happens is you have a shell, okay? You have 1 electron out there. You have 1 proton in here, and that 1 proton is trying to hold on to that 1 electron, and it's having a hard time, okay? I have to laugh. This is sort of like your first kid, you know. They try and hold on to that 1 kid like really hard, and that kid keeps trying to get away. Well, then you get 2, but you have 2 parents. So each kid gets watched. So what happens is as you have more protons in the center, but you haven't expanded your shell, it sucks it in a little tighter. And then you go on to the next shell, and you have 1 in it. Well, you only have 1 more proton, but it's a shell away now. So it's harder to hold on to it. But the more protons I put in the center, the more electrons on that shell, it sucks it in tighter again until I have to add another shell. So it keeps going through that. So going across a row, it actually becomes smaller on the atomic radius. Okay? The other thing that they wanted to know was ionization energy. It is just the opposite. So remember these noble gases? Okay, ionization energy basically is removing an electron. Well, a noble gas has what it needs. You try and take away from me what I need, it's going to get riled up. It's going to get real riled up. These guys over here, they want to be like the noble gases. I have 1 extra. Take that 1 extra so I can be like the noble gases. So this one has a very high ionization. Okay, this one has a very low ionization. Ionization energy. Okay? Francium has, think of it this way, francium has 87 kids. You want one? Take it. Helium has 2. You take one of my 2, man, you're messing with it. Yeah. Okay? So high ionization energy heading towards helium, low heading towards francium. Atomic radius, large. Okay? Down by francium, small, up at helium. Okay, be able to draw an electron dot. This becomes very simple if you look at the periodic table. Remember I drew 1, 2 for your valence electrons, 3, 4, 5, 6, 7, and 8. Remember that? Well, this makes it real easy because when you draw your Lewis dot, 1, 2 opposite because they're negative, it won't be as far apart as possible. 3, whoops, I missed that one. Let's try it again. 3, triangle, far apart as possible. 4, 1 on each side. 5, okay, now we got to start pairing. 6, 1, 2, 3, 4, 5, 6. 7, I'm going to write over here. 1, 2, 3, 4, 5, 6, 7. And noble gases, 2 on each side. Okay? That's the same for anything in that family. So if I put up here SB, how many would SB have around it?
Elizabeth, Reno. Could you please come to the office and today? Thank you.
right? Antimony is in nitrogen's column. It has 5 in its outer shell. So if I'm looking at antimony, I go out to antimony on that row. I ignore the D. I have 2 in the S and I have 3 in the P. Total of 5, right? Okay, last couple of things really quickly. Or last one. Orbitals contain 2 electrons. Remember that. Orbitals only contain 2 electrons. S has 1 orbit. P has 3 orbits. D has 5 orbits. F has 7 orbits. F has how many electrons? 14. D has how many electrons? 10. P has how many electrons? 6. S has how many electrons? 2. You need to be able to have that in your head. Be careful. Okay, because when you say, oh, how many electrons in the 3D, and you don't watch that next word, which is orbit, you might say 10, and the answer actually is 2. Okay, so be careful. Okay? Any other questions you want to ask me really quick? You got 2 minutes.
So everything's due by Monday, right?
Yes, you need to make sure that all your Learn Smarts are done, that all your homeworks are done and submitted. Okay, make sure you're looking on Weber and make sure the score is transferring over. Yes? Yeah, Monday morning I will be here. I usually get here at 6:45. Today I was a little late because of the accidents. That one right in front of Maverick was awful. Did you guys see that one?
No.
There was a boat and a car and
Maverick like down the road?
just over here. The Maverick on 193. That was awful. Okay, I will stop this and I will get it up on